LeetCode problem. So sharing my screen now. Choosing the right layout. Moving here, and I think I also need to set timer. Give me a second. Okay. So I haven't solved this problem before. But based on the rating of this problem, it should be relatively easy. I think we are good to go. Let's start. So there is an undirected graph with n nodes. Each node is numbered between 0 and n-1. And we are giving a 2D array graph, where graph U is an array of nodes that node U is adjacent to. More formally, for each V in graph U, there is an undirected edge between node U and node V. Okay, 2D array. When I'm thinking about 2D array, I'm thinking about array where all of the rows are the same, but here it sounds like some nodes can be connected to more other nodes and some will have less nodes. So it looks like this is a wrong assumption, and rows in this 2D array can be of different length. Okay, let's move on. The graph has the following properties. Okay, actually let me say that graph is a list of they're numbered between 0 and n, so it will be an integer list. Okay. There are no self edges, so there are no edges that go back, no nodes, no edges that go back to the same node that they started it at. There are no parallel edges, so any two nodes are connected by just one edge. Okay, so basically all of the edges are duplicated. If there is one node pointing to another, then another node will be pointing to the first one. Okay. The graph may not be connected. That should be an edge case that I have to discover myself, but thanks for saying. Okay. I will be running tests soon, but not right now. A graph is bipartite if the nodes can be partitioned into two independent sets, A and B, such that every edge in the graph connects a node in set A and the node in set B. Okay. And return true if the graph is bipartite. What gave me a pause is the fact that looks like I'm pausing. I'm also thinking, okay, so first of all, I think there can be a bipartite unconnected graph. So we'll be assuming that because it's basically a combination of two bipartite graphs. They can still be split into two sets of nodes where all edges are going over this separation line, even though there are two separate graphs. Okay, so here will be returning Boolean. And now let's think about this problem a little bit. So let me create some tests. Let's say that the graph is 2, 3. Oh, I already have an idea about how can I be solving this. And it's a breadth-first search, but we'll get to it soon. Okay, we start with 0, so let's say 0. So is this graph bipartite? It is, because if we put it like this, so 2, 3, and then 0 and 1. So 1 is connected to 2, 2 is connected to 3, 0 is connected to 1. So all of those, there is basically a separator that we can draw here between those nodes, and all edges will be going over this separator. But so here we will be returning true. But what about the graph that looks, for example, like this, where we have also another node connecting 3 and 0? Yes, it still can be bipartite, because in the same fashion as we have drawn here, a new node that is added between 3 and 0, it will also be going over the separation line. Let's maybe find some graph that is not bipartite, and it's also kind of simple. So 2, 3, 2, 1, 0. And here, I don't know how should I draw this connection, but let's assume that this is a connection between 0 and 1. And clearly this graph is not bipartite. Why? Because let's say we put node 0 on one side of the graph, then nodes 2 and 1 have to be on the other side of the, sorry, no, let's put 0 on one side of the separation line, and then both node 2 and 1, since they're connected to node 0, should be on the other side, but they are also connected to each other, so that's a contradiction. We cannot make this graph bipartite. And this gives us an idea about the solution and breadth-first search that I mentioned before. But before that, let's think about some corner cases. So for example, can there be, well, we haven't drawn yet any kind of separated graph, unconnected graph, sorry. So let's say it will be 1 and 2, and then separately 0. Can this graph be bipartite? Yes, it can. Actually, let's start with something even simpler. Graph that has 2 nodes, but no edges. So yeah, why not? It can be like this. And this graph is bipartite because all the non-existent edges are going over the separation line. That's fine. What about something like this? Still true. And essentially, yes, we need to just find all the possible for all the pieces of the whole graph. If those pieces are unconnected, we just need to traverse each piece separately. So one of the things that we have to do, okay, yes, we have the length of this graph, of this list graph, will be equal to the number of total nodes that we have. So we can easily traverse the whole graph and figure out which nodes are visited, which ones are not visited. Okay. Yeah, now let's talk about the solution, right? And solution is kind of like coloring of the nodes. So let's say we start with some node and we color it in one of two colors. Let's say we color it in white. Then we go over all the edges connecting this node to all the other edges, and we color all those nodes in a different color, because basically it will be set of A and set of B. And once we go from one node to its neighbor, they should always be in separate sets. So we will call these sets like colors, just for clarity. And we will do breadth first search because each extension of breadth first search should go as a change of color. And then what I'm thinking about is like, what do we have? What do we do with visited nodes? So there can be a situation like, what if there are more nodes? Let's see, there is like a cycle of 5 nodes connected to each other. Um, we will be visiting one node twice. So as here, for example, even one, right? If we do breadth first search, we'll be visiting it first time from 0, and we will color it in specific color. And then we will visit it after visiting 2. And this node is already visited. So we don't need to expand it further. The only thing that we need to check is if this node that is already visited has the color that is valid with the current like new arrival that we have to this node. So essentially, let's say we colored node 0 in white. Then we are traversing and coloring node 2 and node 1 in black. Then we are continuing, let's say we are going from node 2 to node 1. And now we should be, one is already visited, so we just check if it's colored in a valid way. But it's colored in black, and now it should be colored in white. So this is a contradiction, and we can return false for the whole problem. Now, the running time complexity, right? So we will be traversing all nodes and all edges. So depending on what is bigger in this scenario, we will have like O of n plus m runtime, and we will be storing all the nodes, our frontier in a double-ended queue. So we will need to also spend O of n plus m space. The only thing that we haven't discussed, and that will be a corner case for like unconnected graphs. So let's say we have visited these nodes, right? So how do we continue expanding more of those searches? I think the easiest way is just to go through all the nodes that we have, like from 0 to n minus 1 inclusive. And if the node is already visited, we start expanding. We start running this like breadth first search that is coloring the nodes. If the node is visited, we just go on and go through the whole list of all nodes. So we try to start at each node if it's not visited yet. This will fix our problem for like, what if the graph is unconnected and starting at at node 0, we won't get to all other nodes. We will try to start with each of those. Okay, so now that we have discussed the solution, let's quickly implement this. Okay, so what do we need? First of all, we will need visited, and it will be false times, let's call it n length of graph. That's the number of nodes that we have. Visited is false times n, and color equals none times n. I think we don't need this visited because the only way to color our node is by visiting it, and this color can also serve as a visited array. So let's simplify our problem a little bit. Now we will also need a function. Let's call it BFS, and it starts at node. I'm thinking about how should I be creating a list of neighbors. Probably I will just visit all the check all the neighbors, check the current coloring, and yes, I will only add to double-ended queue the nodes that I haven't visited yet. Okay, so BFS, it starts at node. It doesn't return anything, it just mutates the array outside. Okay, should it actually return anything? I probably don't want to continue iterating over nodes if I already know that the graph is not bipartite. Yes, it won't change the runtime complexity, but still, let's say that it returns, this BFS returns Boolean. So it returns true if returns true if the graph is bipartite, else false. Okay, now I think this looks good, and let's try to color. So first color, should we call it white and black, or should it call it like true or false? Because it will be easier to switch colors. I think since we are calling it coloring, let's start with color. I don't, I think it's not elegant. Let's not call it color. Let's call it set. Okay. True set, false set. No, that's also, okay, let's call it color. I digress. Color white. So when we are visiting, we are starting at node. So our double-ended queue will be the queue of node. And then for each, while the queue, for each in length range length of DQ for each of the nodes that are currently in our frontier. What do? We do pop node equals DQ pop. So I'm renaming the node. Will it be a problem? I don't think so. It shouldn't be a problem. So at this point, we are starting visiting the nodes. So color of node equals to, oh, that was wrong. Current color. Because we basically renamed the variable from the outer scope, which is not what we wanted to do. So color of node is current color. And now we need to add all the neighbors of this node to the queue, but we are only adding neighbors that are not visited yet. So for neighbor in ref node, if okay, I'm also thinking about how we check that the color is valid, but let's first figure out if it's colored. If color of this neighbor is not none, and then if is none, then it's fine, and we just add it to double-ended queue, right? The queue append neighbor, else it's not none. And here we are checking if color neighbor is equal to current color, then we return false. That basically means that we need to jump once from this node, from the current node to the neighbor node. So we will need to change the color, but it's the neighboring node is already colored in the same color. So this is a contradiction, and we need to return false for this whole BFS function. But if it's actually different from the current color, we don't need to do anything. So it's already visited, and so far there is no invalid jumps to this node, no invalid coloring. So that's it. The only thing that is left that we need to do every time then that we finish the level. Okay, our time is up. Let's spend 10 more minutes. So back to what I was saying. We now need to update the color. So if current color is equal to white, current color now black, else current color will be now white. Okay, and then finally here, if we have traversed the whole graph and it's still fine, we are not returning false basically, so it means that the whole graph can be bipartite, and we are doing true. Okay, so now the last thing that we need to do is for starting node in range n, if color of this starting node is none, so it's not colored yet, we where we are actually okay, we are coloring our nodes. That's good. So if color is none, then I am thinking, where do we actually want to color our nodes? Because see, maybe we will be adding node several times to our double-ended queue right now in BFS. What if we are arriving from 5 different nodes and we are not checking before adding the node? Before adding the node, it's none, but we are not coloring it right now. So I think we should be coloring nodes when we are adding those to current color, next color equals black. We will change how we approach this a little bit. So if current color equals next color equals white, and here next color equals black. So here, if color of neighbor is none, we are coloring it right away. This we're removing. Color of neighbor is the next color. And here we also need to start already with our current node. Node color of node is equal to so it will be the only one. Yes. Okay. So it will be current color, and we'll be popping. Basically, our invariant before was that all nodes in our double-ended queue are not visited, but now our invariant is that once we are considering the node, we are coloring it right away, and all the nodes in our double-ended queue are already colored, so that we cannot add one node twice to our double-ended queue, because then it would be just like indefinitely increasing it. Not indefinitely, but it complicates things without giving us anything. I actually don't think it would break the algorithm, because yes, we will just, it won't break the algorithm, it won't change the runtime complexity, it will just a lot of unnecessary nodes added to the double-ended queue, possibly. Okay, if color of starting node is none, that's good. Then we run is Bipartite. We are running BFS starting at this node. If not is bipartite, we return false, and again here we return true. Okay, now let's quickly check for this graph what will be going on here. So n will be equal to 3, and color will be right now none, none, none. So now we will be starting node. If starting node first will be 0. So if color of starting node is none, it's none, we will start BFS from here. So we are defining colors in this way, and now double-ended queue only contains one node, which is node 0, and we are coloring the current node right away to white. So now double-ended queue, okay, we are popping this one node, this one is removed, and for neighbor and graph node, we will have two neighbors there, 1 and 2. If color neighbor is none, so color of 1 is none, we will be coloring it next color, so it will be colored in black, and it will be added to the double-ended queue, and then the same goes for the second node, colored in black, added to the double-ended queue. Now, moving on, so we will be swapping the colors. Current color is white, so now current color is black, and next color is white. And we go to the second loop, and here we have two nodes in double-ended queue. So first we pop node 1, and for neighbor, it has two neighbors. It has neighbor 0 and neighbor 2. So starting at neighbor 0, color of 0 is not none, so color of neighbor is current color. No, color of neighbor, current color is black, but not, neighbor is white, so everything is fine. We continue to the second neighbor, which is 2. So color's neighbor is not none, and color's neighbor is black, which is equal to the current color, so we're returning false. So from here we'll be returning false, and here it's not bipartite, so we are returning false, and we never get to return true. It looks good. And we have a bug. Yes, let's suffer a little bit. Okay, so another node, another graph. We're represented by this list. So it has nodes 1, has nodes 1 and 3, and 0 and 2. Okay, so node 0 is connected to nodes 1 and 3. So we have connection here, and we have connection here. Node 1 is connected to node 2. Node 1 is connected to node 0 and node 2. Node 2 is connected to node 1 and node 3. And node 3 is connected to node 0 and node 2. I'm returning false for this. Okay, that's strange. So this is basically, yes, just a cycle graph. Let's see what happens then. So we'll just be running one BFS. It's similar to what we had here, but okay, so on the first loop we will be using just 0, and so first one will be 0, and it will be connected to 1 and 3. So 1 and 3 will be colored in black on this first loop, and then we will be iterating over nodes 1. 1 will be checking 2, will be checking 0, and 0 is fine. Actually, case 1 here with this false, which is correct. Okay. Now it will also be checking, so when we are checking 1, we'll go to node 2, and we will color this white as the next color. Okay, yeah, so the logic seems legit. The problem is that I have messed something up. Oh, yeah, I'm not returning color, so I will never get here. So let's just print color on each. Oops, okay, so here we will never go to the third. Oh, yes, I see. I think the issue is no, I'm wrong. So for node 1, we'll be considering node 2. and it will be none at this point. So we will color it on white, and we will append it to the double-ended queue. Now, then we will be considering node 3, and it also has neighbor of 2, and it's not the same, the current color. Okay, let's modify this case to okay, let's say that node 1 doesn't have node 2, so node 2 doesn't have node 1. Okay, we are here again. So even though the nodes are not connected, this is painful. I need to evaluate this line by line. I want to evaluate this line by line. We are only returning false here. But okay, so here the first node, okay, 3 we're considering. Why is there 2? Oh damn. I figured out what is the issue. It's obviously a very stupid issue. I'm popping from the end and using my queue as a stack. I obviously didn't mean it. Those are the bugs that are the hardest to find. But yeah, now we are done. Yeah, those are the bugs that are hardest to find because you assume that this is correct when you're writing this. So it's very hard to question yourself about this particular point. A lesson for me, I guess. Now let me stop sharing my screen. And I'm stopping the recording. See you all tomorrow.